So today we are going to start from there. We started a little bit about the mathematical background and how to show that this algorithm converges to a stationary point. So I'm going to remind it to you a little bit, and then we are going to go on with this theoretical results. So today will be just theoretical results and proofs for stochastic gradient descent, and hopefully on Wednesday and Thursday I'll try to show you some more examples and experiments on experimentally how these algorithms work, and talk about new algorithms, variants of stochastic gradient descent. So let's remember what we did last time at the very end. So we reformulated our problem. So let me remind you that. So what we are saying is we have a probability distribution which chooses samples for us from an input space and times the output space, and that okay. And what we do is we define C as a random variable, or you may think about it as a random seed with realizations, either a sample from the space of data points or a set of samples, which we call, so it's a set of samples. Either we call it a mini batch sometimes, or the whole training data can be chosen by C. And if you remember, we talked about a prediction function H and a loss function, and these two helped us to train a model such that it gives outputs the right answers, right outputs, by looking at these inputs xi. So it outputs something very close, hopefully close to the real output, correct output yi. So we defined f as a composition of the loss function and the prediction function, and we defined fi as the value of this at a realization ci. So in open form, it is the value of the loss function of the model and evaluated at the output of the model with respect to some parameter omega, and then the output value yi for n many realizations of the random variable c. And this is our data set, and we are looking at this to learn this connection between input values and the output values given with a probability distribution that we don't know. So if we knew the probability distribution, we would be probably able to find the minimum value of the expected value of this function given some parameter omega. But this function is called the expected risk, but we said, okay, we don't know the probability distribution, so it's not easy to solve that problem. So instead, we introduced the function empirical risk. So the value of fi is at these realizations, the average value of the loss functions. So our main problem is actually solving the problem, optimizing, minimizing the empirical risk function. But what we really want is to minimize the expected risk function, which we won't be able to do in general in most of the time. So what we do is we solve minimizing the empirical risk problem. Then we hope that it tells us something about minimum value of the expected risk, or minimum point, which gives the minima omega or for the expected risk. And there are statistical results which connect these two, the minimum values of these two functions. We didn't talk about those, but as I said before, in practice, what people really do is, instead of relying on those statistical relations, they do this. They look at the sample points, and then they divide them into two. Some of them, they call it the training points. Maybe they randomly choose 70-80% of these points as training points, and the rest they call it the test points. And they don't see these points, they don't work on these points. What they do is they try to find the optimum value of the parameter omega such that it gives a local minimizer of this empirical risk function evaluated for the points on the training set. And then what they do is they check how well that minima behaves on the empirical risk function on the test set. All right. So we find the minimum of this function, which we call the training function, in order to find a minima for this testing function. So we don't use it, but we want to find the minimum of this function by just using the training function. All right. So this is the problem. So the problem is a little bit different than classical optimization problems that you find the minimum of a function. Actually, you find the minimum of this function and hope that it gives you a good generalization for this points that we haven't seen, which we call the test points. All right, and we talked about this last time, and we gave some intuition of why stochastic gradient descent works nice on these problems. Let me remind you what the stochastic gradient descent was. So basically, we define this function f of x. We are looking for its global, for its minimum value. This is an unconstrained optimization problem. And here the capital F is either the expected risk function or the empirical risk function. But in this class, it will be nearly entirely the empirical risk function. And then we define this gradient function. It's not just a gradient. This is a stochastic gradient, which is an approximation of the gradient of the capital F. So it is calculated either by just calculating the stochastic gradient at one realization of the KC. So basically you just choose one point from the training set and then calculate the gradient with respect to that data point, or you choose a mini batch of those. Maybe I'm just making 100 at 200. So you just choose a small batch, mini batch of those data points and calculate the average gradient of the loss function on those data points. So both of these can be used in the following analysis that we are going to go over today. So then the stochastic gradient descent was, you start with an initial point given to you, and then we are also given a maximum iteration number, so we are just going to stop there at that point and we'll go until we reach the iteration number t. And then let's assume we are given step sizes alpha k's, or we can generate also them at every step itself, but for now just assume that we have this sequence from the beginning. And then for all these steps, at each step we generate a realization of the KC function, the random variable, random seed, let's say. Basically we are just going to choose one data point or a mini batch of those, calculate this approximate stochastic gradient, and then behave as if it's the gradient of f and do a gradient descent, but now it's called stochastic gradient descent. So we just move in the opposite direction of that gradient with some step size alpha k that is given from the beginning. So this is a very simple algorithm which finds a stationary point iteratively We hope that it finds a local minimum, but actually what we will guarantee today is it will converge to a stationary point where the derivative of the capital F is 0. That's all we can guarantee, at least in the very general sense for non-convex functions. So let me remind you a few definitions. We say omega star is a stationary point of the function f if the gradient at that point is 0. So it's a stationary point. And then we define this L2 norm of a vector. You just square the coordinates and then add them up, take the square root. So it's the standard Euclidean norm. And then, okay, we gave an assumption, if you remember. So we are dealing with these very general functions, non-convex functions. So we need some structure so that we can show some convergence results for stochastic gradient descent. So at first, we are going to do other assumptions today, but our first assumption for today is we are going to assume that the capital F, the objective function, is continuously differentiable. So it's differentiable and its derivatives are continuous. And its gradient is Lipschitz continuous with the constant L, which means the norm of the at any 2 points omega and v, the gradient, the values of the gradient, the difference, the norm of the difference is smaller than L times the distance between these 2 points. That's Lipschitz continuity. And as I told you, this says something, even though we don't assume that this is twice differentiable, this says something about curvature. And actually, if the objective function is twice differentiable, this means it's the second derivative is bounded from above. All right. Let's see. So this is one important. All right. So sorry that the camera moved away. All right. So we talked about Lipschitz continuity. So one important consequence of Lipschitz continuity is this proposition that we have proved last time. Then if f is Lipschitz continuous with the constant L, with the Lipschitz constant L, then for any 2 points omega and v, f of omega is always smaller than equal to f of v plus gradient of f evaluated at v transpose times omega minus v plus L over 2 and the square of the distance between these 2 points. This notation is just stands for inner product of these two vectors. And I explained briefly what it's just. We think all vectors as column vectors, and the transpose means it's a row vector now, and this multiplication just gives us the inner product. Okay, we showed this last time, and using just this Lipschitz continuity, we gave our first result. And okay, I forgot to mention that all these notations that I use and the proofs are basically from the survey paper of Boteau, Curtis, and Nosedal from Siam Review 2018. It's a very nice survey on stochastic optimization for large-scale machine learning. So I really suggest you to have a look at that. You can find much more material there. I'm just changed a little bit, simplified a little bit here. So have a look at that paper. It's full of intuitions and nice results to understand this, to have a nice introduction to this area. All right. So by e ck, we are going to denote the expected value with respect to k given the point omega k. So I'm just going to use this notation without mentioning omega k, but omega k is always there as a conditional expectation. Our first result was this lemma. So if we assume Lipschitz continuity, then any iterate of the stochastic gradient descent satisfies this inequality. So we start at omega k, we calculate the function at omega k, and then we wonder what is the expected value of the function f at the new point wk plus 1, which we calculate by a step of the stochastic gradient descent. So what is the expected value of this function at this new value, at this new point, and what is the difference with the previous point? And actually it is bounded above by this expression. So what we really want is we want this difference to be negative, right? So that at each step we go to a point where the function decreases with respect to the previous point. So, and if you look at this expression, we will use this a lot. Okay, here there are two terms. The second term is always positive. So hopefully the first term is negative, but it starts with a negative. So we want alpha k is positive. So we want this inner product to be positive also, all right? So we want the negative gradient to be a descent direction. All right. So this approximates stochastic gradient. We want the stochastic gradient to be, the negative of that to be a descent direction. So we hope that this is positive, and in our case, it is positive because it can be easily seen that the derivative, the expected value of the gradient is exactly the gradient of f. We haven't used that yet, but okay, we proved this inequality. Now we hope that this is negative, this is positive, and then this whole thing is negative. So to be able to say that unexpected, in expectation, we expect the function to decrease. We want this to be negative, the whole stuff, and this one to be, this is positive, but hopefully this is not very big. So to guarantee that this is decreasing in expectation, we want to bound the second expression here. Especially we want to bound the expectation of the square of the norm of the stochastic gradient. So that will be our second assumption. So we are going to assume that there exists an m, positive m, or 0, or another constant mg, which is bigger than or equal to 1, such that the expected value with respect to k of the stochastic gradient's norm square is smaller than or equal to m plus mg times the norm of the gradient, square of the norm of the gradient. So here m stands for the noise that we cannot get rid of. It is independent from the step we are. It's not going down. It's a constant ratio. It's a constant bound. And then the second term decreases as the gradient, the real gradient decreases. All right. So, and again, m is the noise part of this stochastic gradients. Anyway, so let's assume this is satisfied for each stochastic gradient. Then once we put that assumption, now we can say something about that inequality, something more about that. And it's very actually easy. I'll show you that now we can show that the expected value of the function at the new point minus the value at the old point is bounded by this expression. So it's very easy to see that. So it's just putting those bounds. So what we had before, and then f of omega k, we showed last time that this is smaller than or equal to negative alpha k, the gradient of f, the inner product with the expected value of the gradient plus 1 over 2 times alpha k squared L times the expected value of the norm, squared norm of the stochastic gradient. All right, and what is the expected value of the gradient? Just look at the case where we use only one data point to calculate the stochastic gradient. So what is, okay, so let's say we choose the index I out of from integers from 1 to n, and then we use that to calculate the gradient at the data point xi, right? Okay, what's the probability of choosing I out of all these points from 1 to n? We are assuming the distribution is uniform, so it's 1 over n. So if we add all of these, I goes from 1 to n, we get the expected value. So this is the expected value of the gradient. Let's call it gk. All right, so this is just g of omega k, ck. And this is obviously the definition of the gradient at f. So the expected value of this expression here is just gradient of f. So if you inner product it with the gradient of f itself, so this is just alpha k times gradient of f norm squared. All right, for the second term, we gave a bound on this. And if you put that bound, you have this expression plus L times mg times the norm of the gradient squared. And if you rearrange this, you just get negative 1 minus 1 over 2. I take 1 alpha k out. This term with the norm of the gradient, real gradient. And then plus 1 over 2 times alpha k squared L m. So it's just calculus and a little probability. All right, so we have these two lemmas that we will use again and again. And okay, so let's give our first result on convergence. All right, so let me define the total expectation of f of omega k. It is just taking expected values of all the realizations that we have used since we came up to omega k. So we used all these realizations of the Xi to come up with the point omega k. So you take the total expectation, you define the total expectation like this. And with this definition, now we can give our first result on convergence. So I start with non-convex functions and fixed step size. We are going to look at other variations of this result. So I start with non-convex objective functions because it's the main topic of stochastic optimization in machine learning, because these methods are mostly used in deep learning, these optimization methods. And in deep learning, those prediction objective functions given by the prediction function, they are composed of artificial neural networks, which are highly non-convex, right? So very complicated functions, but still we can give a result on this. And then we look at the fixed step size case first. And in my experience, at least, I think this is one of the most popular ways to run a stochastic optimization method. The first thing you do is you run it on a small constant step size. And how small, it really depends on the optimization methods you use. For Adam, it's usually 0.001. For stochastic gradient descent, it's mostly, in my experience, it's around 0.1 or something like that. But it heavily depends on the problem at hand. So the big problem is which step size, even fixed, which step size you should use. You have to try and see most of the time. There are some theoretical results, but actually in practice they are not really usable, so people try a lot of time choosing even this fixed step size. All right, so under assumptions 1 and 2, let's assume that we run the stochastic gradient method for t many times, and with a fixed step size alpha, and we assume that alpha is smaller than 1 over L times mg. L is the Lipschitz constant, and mg is the constant that we use to bound the stochastic norms of the stochastic gradients, squared norms of the stochastic gradients. And under these conditions, we can show that the sum of the gradients evaluated at each step is smaller than equal to this expression, t times alpha times L times m plus 2 times f of omega 1 initial point minus f of f infimum. It is okay, I just forgot to mention here that we also assume that the function f, in assumption 1 maybe. All right, the function f is lower bounded with f of f inf. Actually, I didn't write it here in these notes. So we assume that the function is lower bounded. And we call it f inf. All right, so f omega 1 minus f inf over alpha. That's our expression. And just using this, if you divide both sides by t, this is what you get. The average value of the gradient's norm squared on these points on the stochastic gradient descent is smaller than equal to alpha times L times m over this expression with t in the denominator, which means if I raise t, if I let SGD run a longer time, the second term will go to 0. So this average value will converge to alpha times L times m. So you are going to converge to a point where the gradient is very small if you choose alpha small, right? So if you want to reach really to a stationary point, very close to the stationary point, so you should choose a smaller alpha so that this converges to a smaller value. So that means you are closer to the stationary point. But then, as you can see, the second expression will go to 0 slower if you choose alpha smaller. So there's always this optimization here where shall I choose the fixed step size big so that the convergence is fast, requires less iterations, but then the point that I converge may be a little bit farther away from the stationary point that I'm trying to converge. I'm staying stationary, but we are hoping that it is a local minimum. All right, so this is our first result. And even looking at this general result, we assume nothing about the objective function and we have a fixed step size. And the convergence is like O of 1 over T, as you can see. And we start to get some intuition of how these methods work, how this stochastic gradient descent method works. All right, let's prove this. We are just going to use the lemma. The proof is short. All right, so we have already proved this in the second lemma, this inequality, that this difference is smaller than or equal to this expression. All right, we are just going to use this. All right, so all we need to do is actually take the total expectation of both sides of this inequality here. Then what we will have, okay, total expectation of f of omega k plus 1 minus the total. Now we are taking the total expectation, so we have to take the expectation of the second term here also. Because before, since omega k doesn't depend on k here, we didn't take the expectation of that. Now, let's see. This is smaller than or equal to, all right, negative 1 minus 1 over 2 alpha. Now, alpha is a constant. We don't have alpha k, it's always fixed. LMG alpha, the expected value of the squared norm of the gradient, plus this constant. All right, but we have chosen alpha smaller than 1 over L times mg, so that these cancel out. So we can say this is smaller than or equal to negative 1/2 times alpha. Then the expected value of gradient of f of omega k plus this expression, this constant again. Now what we are going to do is, okay, we have the term in our sum, the terms in our sum, the expected value of the norms of the gradient squares. Now let's take the sum from 1 to t. Sum over k goes from 1 to t. All right. So if you look at the left-hand side, if you sum this over k, this is a telescopic sum. Only the last and the first term survives. So what we have is the expected value of f evaluated at omega t plus 1 at the last point, minus, I'm not going to use the expected value from now on, in the second term, because omega 1 is fixed, it's the initial point. All right, and the right hand side turns into negative 1/2 alpha. Then the sum k goes from 1 to t. The expected value of the norm, squared norm of the gradient at omega k, exactly what we needed, plus, all right, so the sum of this constant term t many times is 1/2 alpha squared L times m times t. All right, now we just need to, change these terms, rearrange them, multiplying with 2/alpha, both sides. And once you do that, okay, I'm not going to write that. Once you reorder these, leave the sum alone, you get exactly this expression here if you take the expected value outside the sum. So you get exactly this expression if you multiply 2/alpha. Here's the 2/alpha. Okay, one thing that I forgot to mention here is, all right, we assume that the function is lower bounded by f_inf, so I can just lower bound this f_inf minus f of omega 1. Then this is the term that we needed in our proof, in our statement. And the rest is just taking the average, dividing everything by t. So the result follows. All right, so this is our first result for SGD. As you can see, it's simple to prove. But still, it proves that our stochastic gradient descent method converges to a stationary point, or at close to the stationary point, for any function, or for any continuous differentiable, Lipschitz continuous differentiable objective function. So it's a pretty general result. But as you can see, this only converges to a neighborhood of the stationary point, not to the stationary point. And by choosing alpha smaller, you can get closer to the stationary point, but then you move slower because this term goes to 0 slowly. It's slower, right? What you can do is, you can, instead of choosing a fixed step size, you can choose a sequence of step sizes that diminishes, which converges to 0. Then you can actually prove that this average values of the squared norms of the gradients actually converge to 0. So to get this result, we are going to assume that we have a diminishing step size sequence. And all right, let's see. We want the sum of these diminishing step sizes add up to infinity. Let's assume it's an infinite sequence. And I misprinted here. The sum of the squares is finite. So if you choose alpha k as 1/k, this will work. All right? Right? Because sum of 1/k is infinite, but 1/k squared is finite. Then under this assumption and other two assumptions we had, alpha assumptions 1 and 2, then the iterations of the stochastic gradient descent run with this sequence of step sizes satisfies these results. Okay, I'm defining AT as the sum of these step sizes from 1 to t. And I let run SGD for t many steps. Then the sum of the gradients, the sum of alpha k times the gradient squares of the objective function. Actually, the limit is finite, right? It converges to a point. And because of that, if I divide both sides, if I divide this by 1 over AT, and since I know that AT is the sum of alpha k's and AT goes to infinity, this average goes to 0, right? So at first, this seems like, okay, choosing a diminishing step size is better because now we are converging to the stationary point. But in practice, actually, in classical optimization problems, this is useful. But in machine learning problems, you are taking too many steps, and choosing any diminishing step size like this, actually, the step sizes will go to 0 too quickly because we are using a lot of steps. And in practice, in my opinion, in general, I guess, but this is not useful for large-scale machine learning problems. All right, but it gives us an intuition of what's going on. But as much as I could see in my adventures in machine learning, choosing a diminishing step size is not really useful, at least with these rates. Right? Again, sorry for the typo. This should be alpha k squared. The sum of the alpha k squared should be finite. With these rates, this SGD is not really useful. But let's prove this. All right, I'm going to use this inequality again, that we use the second lemma that we introduced and taking the total expectation of that result in the second lemma. And instead of alpha, I'm going to use alpha k. So using the lemma 2, we have, and taking total expectations. This is smaller than or equal to negative, okay. 1 minus 1 over 2 alpha k times LMG alpha k expected value of squared norm of the gradient of f plus 1 over 2 alpha k squared L times M. All right. And let me write here, since alpha k goes to 0 as k goes to infinity, without loss of generality, we are going to assume that alpha k is smaller than or equal to 1 over L mg, right? We can assume that. So this is smaller than or equal to, again, the same expression as before, but alpha k instead of alpha. And again, summing over k from 1 to t. Again, the same thing, f inf minus f of omega 1 is smaller than or equal to the expected value of f of omega t plus 1 minus f of 1, f of omega 1. All right. Now we cannot take alpha out, so it stays as a weighted sum here. And again, plus 1 over 2 alpha k squared L m of t. Sorry. Now we don't have a fixed step size, so we have plus 1 over 2 times L times m times the sum of alpha k's. Square. Okay, it's good that we have a square there, because we assume that the sum of the squares is finite. All right, so the right-hand side is a finite sum. So after you rearrange this, you can see that, okay, let me write it down. So if we rearrange this, then we have k goes from 1 to t, the expected value of the gradients squared is smaller than or equal to 2 times f of omega 1 minus f of f inf over alpha. Let's see. Adjust that actually. Plus m lm, the sum of alpha k squared. All right, so, sorry. So if we rearrange this, we have this expression. I always forget to check the screen if the camera is following me. But all right, the right-hand side, this is just a constant. And this is because of our assumption on the rate of decreasing of the step sizes, this is also finite. So this gives us the first result. And then what we do is we divided both sides by 1 over AT. And AT is the sum of alpha k's up to t, capital T. And since we assume that it increases without a bound, it goes to infinity, then this goes to 0 as t goes to infinity. All right. So we have a result where this goes to infinity, not to even a small value. All right. So this is our second result that we had today. So one thing before I give a break is a direct consequence of this theorem that, okay, this limit is finite, means this is summable. Therefore, lim inf of the expected value of these gradients should be 0. There should be a subsequence converging to 0. Otherwise, if these gradients stay bounded away from 0, that would mean that you can take it out as that constant, and this gives us a contradiction because the sum of alpha k's is infinite. So this should be infinite in that case. So since sum of alpha k's is infinite, there should be a subsequence of these gradient norms that converges to 0, so that this is finite. So this is our first corollary. I'm going to give 2 more corollaries, but I'll do that after a break. Welcome back. So last time, we gave 2 convergence results for very general non-convex functions without any assumptions on the function except Lipschitz continuity and differentiability. The Lipschitz continuity of the derivative, actually. All right, and we gave 2 results, one for fixed step sizes and one for diminishing step sizes. And then we gave a corollary of that. This is a weak result on the convergence of the norms of this gradient of f, expected value of that. And we can say that under these conditions, with diminishing step sizes, the lim inf of this goes to 0. Actually, we can give stronger results on the convergence of these to 0 to a stationary point. But we have to assume some more. But before assuming something more, I want to give you another result on this. Again, non-convex objective function diminishing step sizes, and under the assumptions of Theorem 2, nothing extra, we can also say this, another kind of result. Instead of looking at the last point, the value of the gradient of the last point, let's assume we let the SGD method run from t many steps, and then we choose a point, an iteration in between randomly, but not uniformly. We choose it with probabilities proportional to the step sizes. What does that mean is, so we want the probabilities to be proportional to the step sizes, but we want a probability distribution. So probability of choosing the step k would be, after running the algorithm t many steps, is just this. So this is a constant, the sum of alpha k's. So it's proportional to alpha k, and if you add these up, you get 1, so it's a probability distribution. So with this distribution, choosing the kth step, then what we can show here is actually, instead of a lim result, the gradient of f evaluated at this randomly chosen point in this sequence of iterates. The expected value of that goes to, is the norm of that, not expected, the norm of that goes to 0 in probability. What does that mean? Let's remember convergence in probability. And then I'm going to remind you the Markov's theorem, inequality from probability classes. Then we are going to use that to prove this result. So if you remember, let's say xn's are, xn's comes from a sequence of random variables. We say xn's converge to a random variable x in probability if and only if, for all epsilon bigger than 0, the probability of x n minus x getting a value bigger than epsilon goes to 0 as n goes to infinity. This is what convergence in probability means. Right, we want to show that for the norm of the gradient of f at the point which is chosen randomly from this sequence. All right, with probability is proportional to alpha k, of course. All right, so to prove this, we need to remember Markov's inequality. So if x is a random variable bigger than or equal to 0, a is positive, then the probability of x getting a value bigger than or equal to a is smaller than or equal to the expected value of x over a. So we will use this. So let's look at this expression. The probability of norm of the gradient of f evaluated at omega k. The probability of this being bigger than or equal to epsilon. Yeah, all right. So let's square this expression. This is the same thing as the square is bigger than or equal to this epsilon squared. And by Markov's inequality, this probability is smaller than or equal to epsilon to the negative 2 1 over epsilon squared times the expected value of this positive random variable. Okay, yes. So this is our random variable, which is positive because it's the norm. And all right, so this is all right. So how do we calculate the expected value? It's the total expectation of this, but total expectation is not enough because it comes to, if you remember, it comes to up to ck minus 1. So we need another expectation with respect to step k, let's say. And all right, so 2 expectations. So this one is the last one. Then gradient of f omega k. All right. What is this expected value? So the question is, what is the probability of choosing k as my iteration that I choose randomly? It's proportional to alpha k, if you remember. So this is epsilon negative 2 alpha k over, maybe I should write I goes to alpha I times this, the probability of getting this value times the value. So this is the expected value with respect to k. But okay, this is just a constant because I run the method for k steps, then I do this selection, random selection procedure. Okay, I can just take it out. All right, this is just a constant. Then the expected value alpha k times gradient of f But if you remember, we showed that the sum of these is bounded above. So this is a term of a converging sum. Then that means if the series converges, the general term should go to 0. So this means this goes to 0 as k goes to infinity, since this is just a finite, this is just a constant value. And this is the term, general term of a converging series. Right? So this is exactly what convergence in probability means. So we have our second result, second corollary, again for diminishing step sizes. All right. So I'll show you one more corollary. Okay, so we have one limit result for the gradients. So we really want them to converge to a stationary point, right? So we show that for diminishing step sizes, kind of the sum converges to 0. But what about the general term? What about this? We show these two weak results of that. And actually, we can show more. We can show a real limit, but we need more assumptions. So under assumptions of theorem 2, and an extra assumption is f, the objective function, is twice differentiable, and this mapping, which takes omega to gradient of f of omega norm squared. We are also assume that this is Lipschitz continuous. Then under these extra assumptions, we can say that the expected value of the norm of the gradient goes to 0. Right? So this is a stronger result, but we need more assumptions. So let me prove this. All right, again, we assume that we are assuming step sizes diminish with that rate. The sum is infinite, but sum of the squares is finite. We have assumptions 1 and 2. And let's say we have this extra assumption of that this map is Lipschitz continuous and f is second differentiable. So let's use all of these to prove this result. So let's define this function g of omega. So it's this map that we assume Lipschitz continuity of is the norm square of this. And of course, this is just the inner product of the gradient of f itself. All right, then we can just now calculate the gradient of g. It is just, if you know some vector calculus, it's just 2 times the gradient of f of omega k, and then times the Hessian, the second derivative of the objective function. All right. So now let's look at this expression. The value of g at 2 consecutive steps. Since we assume g is Lipschitz continuous, let's say with the Lipschitz constant Lg, then okay, we had this proposition that this is smaller than or equal to gradient of g transpose times omega k plus 1 minus omega k plus 1 over 2 times the Lipschitz constant of G, and then norm of k plus 1 minus norm squared. All right, again, what is the definition of, what's the difference between the omega k plus 1 minus omega k? All right, so this is just negative alpha k, the gradient of G and omega k, inner product G of omega k, k plus 1 over 2 LG, oh, sorry, let me take out alpha k squared, G of omega k, k. All right.